students, this is Ms. Shim, and today I'm going to be talking about experimental design, graphing, and chi-square analysis. So if these are topics that you're interested in reviewing or learning, stay tuned. And I'm going to try my best to figure out how to do chapters, or I'll have like the timestamp below in the description box. Okay, so let's get started. Again, we're going to be talking about experimental design, graphing, and chi-square analysis. Let's start with experimental design first. So in science, whenever we do experiments, we have to make sure that our experiments are designed in such a way that it's a controlled experiment. And a controlled experiment has several different properties. You have to make sure that you have a workable hypothesis, a testable hypothesis. You need to have two different types of groups. You need to have a control group. A control group is the group where you are using it as a standard, you're using it as a comparison, and the experimental group is the group that's actually going to receive the treatment that you're testing. You also need to have a couple of different variables. The independent variable, that is the variable that you are changing. So one way to remember this is that in the word independent, you've got, it starts with I, right? And so think of it this way, like I change. This is part of the experiment that you change. Like you change the temperature, you add the medication, okay? And then for the dependent variable, it is what it sounds like. It depends on the independent variable. This is the results of the experiment. This is what you're measuring in the experiment, okay? So you need to have those two variables in a controlled experiment. The next thing that a controlled experiment needs to have is constants or controls. You know, when you want to test what the independent variable is doing to your groups, the experimental group, you really need to make sure that the control group and the experimental group have exactly same conditions. You want to make sure that constants and controls are exactly the same. So for example, if you're testing medication, you want to make sure that the two different groups, control group and the experimental group, have the same environmental impacts, or maybe they have the same lifestyle, they're people of the same age. You want to make sure that there's nothing that's going to influence the results of your experiment. So constants and controls have to remain exactly the same. So here's an example of an experiment. A plant was placed at various depths of water in an aquarium, and light shone on it from above to allow for it to photosynthesize. When aquatic plants undergo photosynthesis, they produce oxygen, which will be released as bubbles by the plant. The number of bubbles that the plant produced in a minute was recorded at each depth in a table. In this example, what is the hypothesis? Remember, the hypothesis has to be specific, okay? And if we're putting a plant at various depths of water, the closer that it is to the light, photosynthesis is going to increase, which means that it's going to produce more oxygen bubbles, right? And so if the plant is placed further down in the water, then it's going to be away from the light, and it's going to decrease photosynthesis and produce less bubbles. Then our hypothesis would be that if our plant is at a shallower depth of water, it's going to have more light, and it's going to do more photosynthesis, and it's going to produce more oxygen. Versus if the plant was placed at a deeper depth of water, then it's not going to be exposed to as much light, photosynthesis will be decreased, and it's not going to produce as much oxygen. And so what's the independent variable? What are we changing? What are we manipulating? And it's really the various depths of water, okay? So the various depths of water, that's what we're changing. And the dependent variable, again, is dependent on the independent variable. This is what we are measuring. And in this case, we are measuring the amount of oxygen produced, the number of bubbles. So that would be the dependent variable. And so what should be the control group? This one's a little bit tricky because we are placing the plant at various depths. So you could choose one of those depths, you could choose one of them and use it as a control, as a comparison for all the other depths of water. Maybe either higher up or deeper down in the water, okay? But the control group would be one that you would choose as a comparison. So what's our prediction? Very similar to our hypothesis in that if plants are at a deeper depth of water, there's not going to be a lot of light, so therefore the plant is not going to undergo photosynthesis as much. The rate of photosynthesis will be pretty low, therefore it's not going to produce as much oxygen. Okay? So here's another experiment about Daphnia. Daphnia are small water fleas they have transparent bodies, so you could actually see all their organs inside. My face is kind of hiding it, so let me just move it out of the way so you could see here. That's the Daphnia, okay? So if we want to measure the heart rate, we could actually see the heart beating. And in this experiment, we are testing how different drugs impact the heart rate. So what could be our hypothesis here? In this case, because we are testing multiple different drugs, we could say that drugs have an impact on the heart rate of Daphnia. Okay, and so what's the independent variable? The independent variable is right over here. Okay, it's the different medications, the different drugs. That's what we're changing. And then what is the dependent variable? What are we measuring? We're measuring the heart rate, which would be all of these different numbers. Okay, and what's the control group? When you look at the different types of drugs that are at the top here, the control group would be water, because water is not technically a drug. Okay, so this would be our control group that we're going to use as a comparison. And so when you look at, even just looking at the data here, adrenaline, right? In general, adrenaline does impact the heart rate of these water fleas. It does go up, right? Whereas look at alcohol. Alcohol, generally, the trend that it goes down. Okay. Okay, next topic is graphing. And here are some of the rules of graphing. You need to have a title, and then you need to determine what type of graph that you're going to make, either a line graph or a bar graph. A line graph, you're going to make a line graph if there's a change in something over time or a continuum. And then you're going to make a bar graph if you're comparing groups or categories or individuals. And when you graph, the independent variable is always on the x-axis, whereas the dependent variable is always going to be on the y-axis. And then when you scale these axes, make sure that they're scaled proportionally. And then remember to always label your axes. You want to include the units, okay? So here is an example of some data. Title is Average Number of Mitochondria in Plants Exposed to Normal and Elevated Levels of CO2. So oftentimes when you look at the title, you can already figure out what is the dependent variable and what is the independent variable, okay? So it says average number of mitochondria, average number. So that kind of tells you that that's what we're counting, that is the dependent variable, that's what we're measuring. Exposed, okay, so that's what we're changing to normal and elevated levels of CO2. That would be our independent variable. Okay, so looking at the table, we've got species 1, 2, 3, all the way to 6 mitochondria at normal CO2 levels per 100 micrometers square of cell area, plus or minus 2 SEX, or the mean. Mitochondria at elevated CO2 levels, okay? So these numbers right here, these are the results. This would be the dependent variable. This is the results, okay? The independent variable would be normal CO2 levels, elevated CO2 levels for species 1, 2, 3, 4, 5, and 6. So are we going to be doing a bar graph or line graph? Because these are individuals, okay, you're comparing, it's going to be a bar graph. The independent variable is going to be normal CO2, elevated CO2 for species 1, 2, 3, 4, 5, 6. And then what we're measuring is the number of mitochondria. That's the dependent variable. Okay, so here is an example of what it's going to look like. I apologize, it's not the best quality picture here. But again, the dependent variable, it's what we're measuring. It's always on the y-axis. It's the number of mitochondria. And then also don't forget your units per 100 micrometers square of cell area. And then it got kind of cut off here, but down here it does say species. So species 1 through 6. And then here's a legend that tells you mitochondria at normal CO2 levels is going to be the lighter bars, and then the darker bars are going to be the mitochondria at elevated CO2 levels. Okay, so that's how we would graph that data. Now, and this one kind of got cut off as well. The title got cut off, but it's okay. What type of graph are we going to do here? Just by looking at this, I can see that there are individuals in this generation. So that tells me that's probably going to be a bar graph, okay? Because we're comparing individuals, and it looks like, what are we measuring? We're measuring average blood glucose levels. That's going to be our dependent variable, okay? That's going to be our dependent variable. That's what we're measuring. And then the independent variable is what's different. It's these individuals and in generation 4, okay? So then you're going to have the generation individuals down here, okay? So like 4-1, 4-2, 4-3. Those are the individuals, and then you would label it individual. And on the y-axis, you would write average blood glucose level. Sorry, my writing is very messy. And then you would include the units, which is mg per deciliter plus or minus 2 SEX. Okay? So that's how you would graph that one. And then look at this one. The table title is Carbon Fixation by Rubisco under different temperatures. Okay? So what are we changing? We're changing different temperatures, right? So that's going to be the independent variable. Probably the dependent variable, what we're measuring is carbon fixation, okay? So this right here is the dependent variable. This right here is the independent variable. However, we got to figure out, is this going to be a line or is it going to be a bar graph? Some of you might be thinking that it's a bar graph because you have different temperatures, like they could be different groups. Okay, but in this case, when I look at the temperatures, it is ascending. It's going from 25, 30, 35, 40. So it's a continuum. It's a continuum. So therefore, this is going to be a line graph. Okay, line graph. And in a line graph, you can include the plus or minus 2 SCX, the 2 SC standard error of the mean. Okay, if this is going to be a line graph, let's just say that this is at this point, this is going to be, 25 degrees, and then let's say that this is 91. Okay, this is point 91, so that's where this point is going to be, plus or minus 9. Okay, so you're going to go up 9, and then you're going to go down 9. Okay, so you're going to go up to, let's say, 101, because, you want the scaling to be even. This is going to be 81. Okay, so it's going to go down to like, plus 9 is going to be 100, so this is point 100 right there, and then down here, minus 9, that's going to be 82, okay? And this point right here is 91. So that's how you draw the 2 SEM bars, plus or minus, okay? So why is that standard error of the mean, those bars, so important? Why is it? Well, looking at this very simplistic graph that I made, this is the average number of jumping jacks per minute student A versus student B. And when I look at this, I can see that student B is better at doing the number of jumping jacks per minute. On average, they have it looks like maybe 55 jumping jacks per minute, whereas student A can do about an average of 40 jumping jacks per minute. So when I compare the two bars, it does look like student B is better at doing the jumping jacks than student A. What's missing from this graph is the standard error of the mean bars, okay? So if I add that in there, then that tells me a little bit more information about how these two students compare, right? So again, the top of these bars is the average. It's the average. But what is the standard error of the mean? It kind of gives us a better idea of the spread of the data. Okay, the spread of the data, the variation. So student A, let's say that they did jumping jacks. They did this task of jumping jacks per minute, like maybe 20 times. Okay, they maybe did this 20 times. Student B did it 20 times as well. Maybe on the first try, they did amazing. They did like 45 jumping jacks per minute. maybe at the end of the day or the end of the 20 tries they were super tired, so they only did maybe 35 or something. So this is, the error bars show you the variation of how they performed in the jumping jacks. Whereas student B, you could see that they had a lot of variation, okay? And notice how the top of this error bar, okay, it does overlap just slightly with the lowest part of the SEM error bar here, okay? So there's a little bit of overlap. And that shows me, because there's overlap, student A and B, there's not a statistical significant difference between the two, okay? There is a slight difference, but it's not significant, and we say that it's not significant because there is overlap. There is some points in their 20 different trial times of doing jumping jacks, okay? The two students were equal, okay? Maybe student A did better at some times than student B. So there is not a significant difference between student A and B, okay? So in science, in biology, okay, when we see these two SEM bars, these standard error of the mean bars, if there's overlap, then we say that there is no statistical significant difference between the two groups if there's overlap, okay? If we're given a table where it says SEM, we need to multiply the SEM by 2, okay? Because when we graph it, we have to graph the 2 SEM. 2 SEM is equal to what we call the 95% confidence interval, CI, okay? And what that means is that we are confident that the actual mean, the real mean, is somewhere in that range, okay? So we multiply it by 2. So this SEM, we multiply by 2 when we graph it. We multiply it by 2, 2, 2, and 2 when we graph it. We don't graph the SEM, we graph the 2 SEM, okay? The error bars here is the 2 SEM, okay? And so let's answer some questions just analyzing this data. In which group, A through E, would you see the largest variation of data? Okay, and again, the 2 SEM bars show you variation. And you could look directly at the height of these standard error bars, or you could just look at the data table, and it looks like soil type B had the most variation, 2 SEM. Okay, so yeah, and it goes all the way up here and all the way down there. Whereas group D, and that's our second question, has the smallest variation of data. It has 0.5, and when you graph it, it's multiplied by 2. So it's 1 up, +1, and -1. Okay, and it has the smallest variation. So identify 3 soil types that had the same effect on plant growth, no statistical significant difference, okay? And so when we're looking for groups that have no statistical significant difference, we're looking for overlap. And it looks to me like B, C, and E have overlap, right? So like C definitely overlaps with E, okay? And then like definitely C overlaps with B, as does E overlaps with B. So I would say B, C, and E, there's no statistical significant difference between those 3 groups because there's overlap. And then name 2 groups where the difference is statistically significant. That's where you would see no overlap. I do not see overlap between D and E, right? They don't overlap. Also C and D, also B and D, okay? And then also A and E, right? A and E, there's no overlap between A and E. All right, so our last topic today is chi-square. And when we do experiments in science, we use chi-square analysis, statistical analysis, to determine if there's a significant difference in the observed data with what we expect. You know, in science, when we design experiments and we make hypotheses, we have an idea of what to expect. We don't just do experiments with no idea what to expect. We kind of have an idea of what the results are going to be. So that is the expected data. We have an expectation, but what we actually observe maybe a little bit different from what we expect. So then we will do a chi-square analysis, statistical analysis test to see if there's a huge difference, a statistical difference between what we expect and what we actually observe. That's the whole point of a chi-square analysis test, is to really see, to give us a numerical, analytical result. And it tells us whether or not there is a big difference or no difference at all between the observed and the expected. And when we do these experiments, we always have to have a null hypothesis, okay? And the null hypothesis is always going to say that there is no statistical significant difference between the observed and the expected, okay? It got kind of cut off at the top, but I think you can read it with me, okay? A student wanted to test whether or not pill bugs or roly-polies are attracted to sugar. To do this, the student set up a choice chamber, see picture below. On one side of the chamber was a cotton soaked in sugar water. On the other side was a cotton ball soaked in regular water. The student placed 30 bugs into the middle of the chamber. After 30 minutes, the student counted how many pill bugs were in each chamber, in each area of the chamber. Okay, so the null hypothesis always states that there is no statistical significant, I'm just going to abbreviate there, difference, okay, between the observed and expected data. And in this case, I want to be a little bit specific about the pill bugs. I'm going to give a reason, because the bugs have no preference, okay? The bugs have no preference for sugar or water, okay? So what we would expect, if there's 30 bugs, okay, we would expect 10 to be in the sugar water, 10 to be in the middle, and 10 to be in the plain water. There's no preference, so they're just going to be evenly spread out after 30 minutes, okay? And so if that's what we expect, and this is what we observe, the numbers are different. 10 versus 14, 10 versus 7, 10 versus 9. Like in your opinion, you might be thinking, that's not very far off, right? 10 versus 14, 10 versus 7, 10 versus 9 especially is not very far off. But that's your opinion. What we do in science is we need to know statistically if there is a significant difference between 10 and 14 and 10 and 7, 10 and 9. So that brings us to the chi-square analysis formula, okay? And this is our chi-square analysis formula. This symbol is chi-square, okay? So we're going to be calculating the chi-square value, okay? It is equal to sigma, which means the sum of observed minus expected squared divided by the expected, okay? And you know, on the AP exam, if you ever have to do this, if you ever have to calculate the chi-square, they're probably going to give you an easy table to fill in. Okay, not all the time. So this is sugar water up here, and then this is regular water. Okay, so what you do is you fill out the table. You're going to need a calculator, okay? But O minus E, that's going to be 4. O minus E, that's going to be 3. Negative 3, actually. And then negative 3, and then negative 1, okay? And then when you square it, you get 16, 9, and 1, okay? And then when you take those values and you divide it by the expected, okay, you get 1.6, 0.9, 0.1, and again, chi-square is the sum. Remember that symbol, sigma symbol? It's a sum of these values, okay? So you use your calculator, and then you add them all together, and then you should get 2.6, okay? So we have 2.6. 2.6 is our chi-square value. So what does that mean, okay? Because what we want to do is we want to know if there's a statistical significant difference between 10 and 14, 10 and 7, 10 and 9. But what does this 2.6 mean? what we're going to do is we're going to use that number 2.6 and we're going to compare it to what we call the critical value, okay? The critical value, you can think of the critical value as being a standard, okay? If our chi-square is bigger than the critical value, that means that there's a statistical significant difference between the observed and the expected. If our chi-square value is bigger, if it's a big number compared to the standard, then that means there is a big difference between observed and expected. There's a big difference, okay? Whereas if our chi-square value is smaller than the critical value, than that limit, okay, then there is not a statistical significant difference between the observed and the expected, okay? So if our critical value, if our chi-square value is smaller than the critical value, then that means there's not a significant difference between the O and the E, the observed and the expected. But if our chi-square value is bigger than that critical value, than that standard, then that means that there is a statistical significant difference. So once that chi-square value is calculated, you're going to compare it to the critical value. And like I said, the critical value is what you compare the chi-square value with. Here's a screenshot of what the chi-square value table looks like. When you take the AP exam, you'll see a formula sheet. And in here, you're just going to draw your eyes to the p-value, okay? P-value. You're going to ignore the 0.01 row. You're going to ignore that. You're only going to be looking at the p-value of 0.05, okay? And then the next thing you're going to look at is the degree of freedom. The degree of freedom is basically the number of categories that you are studying minus 1, okay? So the degree of freedom is the number of categories minus 1. So going back to our experiment here, there are 3 categories. That's sugar water, middle, and plain water. There's 3 categories. So therefore, our degree of freedom is going to be 3 minus 1, which is 2. Our degree of freedom is going to be 2. So going back to this table, therefore, our degree of freedom is 2. Therefore, if you look under the 2, our critical value is 5.99. Again, what is this critical value? It's it's the number that we are comparing chi-square to. It's like the limit. If our chi-square is bigger than 5.99, that means the observed and the expected data, there's a difference. There's a statistical significant difference between the two. But if our chi-square value is less than 5.99, then there is not a huge statistical significant difference between the observed and the expected, okay? So like chi-square, it was 2.6, and 2.6 is less than 5.99. Because it's smaller than 5.99, that means that there was not a huge statistical significant difference between the observed and the expected, okay? It was less than 5.99. Therefore, there's not a statistical significant difference between the observed and the expected. Therefore, our null hypothesis, okay? Therefore, our null hypothesis is not going to be rejected, okay? So we're not going to reject it because remember what our null hypothesis stated? Our null hypothesis stated was that there was no statistical significant difference between the observed and the expected. And that's true because our chi-square value is less than the critical value. It is less than 5.99. So we're going to fail to reject. We're going to fail to reject. Basically, fail to reject means to accept our null hypothesis. Okay? But we don't really say accept. We say fail to reject. Okay? Let's do another example. Okay? A new species of fish is discovered in the deep ocean. After studying and breeding the fish in a lab, scientists noticed that the majority of the offspring are male. Of the 88 offspring they produced in the lab, 52 are male, 36 are female. Perform a chi-square test to determine whether or not this difference is likely due to random chance. Okay, so what we observed is 52 male, 36 female. What would we expect? Half and half. And what is half and half of 88? It's going to be 44 and 44. Okay. Before we continue and do the chi-square table here, for doing our calculation, what is the null hypothesis? There is no statistical significant difference, okay, between the observed and expected. Okay, we should have half male and half female. Okay, so then if our chi-square value is less than, if this number right here is less than the critical value, then therefore our null hypothesis is accepted. We fail to reject it. Okay, so let's do the math. O minus E, okay, is 8. O minus E is -8. And when we square it, it's 64. And then the last thing we do is divide our number by the expected, divide it by 44. And we get 1.455, and chi-square is the sum. It's a sum of these values, which is 2.91, okay? And going to our critical value table, we're gonna look at our degree of freedom is, what is our degree of freedom? Remember, it's the number of categories minus 1. Therefore, our degree of freedom is 1, okay? Therefore, our critical value is 3.84. Again, guys, remember the critical value is what we are comparing our chi-square value to. This is our limit. The critical value is our limit. If our chi-square value is less than, then that means our null hypothesis is accepted. It's we're gonna fail to reject it. Okay, so it's 3.84. So our chi-square value is less than the critical value, therefore we're going to fail to reject. What that means, fail to reject our null hypothesis. What that means is that our null hypothesis is correct, that there is no statistical significant difference between observed and expected. There is not a statistical significant difference between 52 and 44, 36 and 44, okay? So like in your opinion, when you see these numbers and you compare the observed and the expected, you might be like, there's a big difference. There's a big difference between 36 and 44. But statistically, when we calculate it, it's not a lot. It's not a big difference, okay? There's not a statistical significant difference, okay? So we're going to fail to reject. Okay, so that is the 3 topics that I wanted to discuss. I hope that this video was helpful to you. I hope that I was able to make things a little bit clearer. If not, feel free to send me a message. And again, I'll try my best to include chapters or timestamps below in the description box. Okay? All right, have a good day, and I will see you later. Bye!